Today we'll take a short detour and talk about linear independence of characters. Okay, so here are the definitions. So let G be a group, not necessarily finite, and F a field. So by a character we'll mean the following, or maybe just to emphasize the field, an F character of G is a group homomorphism. It's a group homomorphism, let's call it chi, from the group G to the group F cross, which is the multiplicative group of the field. So this is the field, delete the origin, think of it as a group under the multiplication. Okay, so this is the definition of an F character, just a group homomorphism from G to the multiplicative group of the field. And here's the theorem. It says that if I have a collection of characters chi1, chi2, chi-n, let's say chi1, chi2, chi-n be pairwise distinct characters F characters of a group G, then the chi I are linearly independent, okay, 1 to n are linearly independent over F. So what does that mean? Okay, in other words, if I take a linear combination, so other words, if I take summation ai chi I equal to 0, okay, so what are these now? Chi i's are all interpreted as functions from the group G to the field F, and when I say summation, I just mean pointwise summation for some ai, so this is 0 for some elements ai of F, then this implies that all the ai's must be 0. So this is the usual definition of linear independence. The only little thing that requires explanation here is what we mean by this summation. You know, what do you mean by a linear combination of characters? So note, what we are probably thinking of is the following vector space. So let me just call it maps from G to F. Okay, what is this? It's just all functions, set maps. Don't put any further structure on anything. Look at all set maps from G to F. Just a map of sets, okay, such that F is a map of sets. So this collection of all maps is in fact a vector space under F, is a F vector space. Okay, what I mean is I have a notion of addition and scalar multiplication which satisfies the axioms. How do you add two maps? Well, you just add them pointwise. So how do you add? If I have F1 and F2, which are both maps. In fact, I don't even need G to be a group for all this. Any set will do. Then I define F1 plus F2 pointwise to be just this. And how do you scalar multiply F1? Let's say also use F. So if I multiply F by a scalar lambda from the field F, this is just I apply F to G. It's now an element of the field F and I multiply it by lambda. So this is now for all lambda in F. So these are the definitions. This is how addition and scalar multiplication of maps are defined, and under these, I mean, it's easy to check that with these definitions it forms a F vector space. Okay, and so when we say linear independence here, what we mean is this linear combination is thought of as an element of this vector space of maps. think of this as now a map from G to F, which is basically pointwise linear combination, right? On every element of the group G, you just have to compute summation ai chi I of G. Okay, so in this vector space, this is a set of linearly independent elements. That's the content of the theorem. Okay, so let's prove this now. So the proof is by induction on n. So I'm just going to do this by induction. So for n equals 1, this is trivially true. Why? Because a single character, so if I only have one character chi1, then that character is not 0. Okay, a character is definitely a non-zero map. Why? Because its range is actually inside f minus 0, right? Because chi1 is such a map, therefore chi1 can't be the 0 map. Okay, the 0 map is the one which takes all the elements of the group to the element 0 of the field. So therefore chi1 itself is linearly independent. Just put Li for linear independence. Okay, so now let's assume that this holds for n minus 1. Assume the induction hypothesis that assume this is true for n minus 1. So let's take n to be at least 2 for this. Okay, so when I say assume true for n minus 1, I mean for any collection of n minus 1 characters. Any collection of n minus 1 characters is assumed to be linearly independent. And now we need to show that any collection of n characters is also linearly independent. Okay, so suppose not. So to prove the claim for n, let's proceed by contradiction. Suppose not. What does that mean? It says that there exists some linear combination which is 0, right? So there exists scalars, there are elements ai in f such that this linear combination ai is 0. Okay, and recall what that just means is the pointwise sum ai chi I of G, it gives me 0 for all group elements G in G. Now observe that because of the induction hypothesis that every n minus 1 among these n are linearly independent, right? So by the induction hypothesis, maybe we'll give it a name. So we'll say, since this is, so I'll call this star, okay, the hypothesis. By the induction hypothesis, what we conclude is that none of the AIs can be 0. Because even if one of them is 0, what you would obtain is a linear dependence relation among n minus 1 or fewer of these chi-i's. Okay, but we know that no n minus 1 are linearly dependent. Okay, so that's the conclusion. All the AIs are non-zero. That's what we know. Okay, now let's see. So this little relation here is what we need. Okay, we know that this linear combination is 0, and what we are going to do is to substitute in place of G, we will substitute GH. Okay, so let's keep this intact. Let's copy. So here's what I know to be true. Okay, so this is true for all G in G. Okay, so in particular, it's true if I replace G by the element GH. Okay, so I'm going to replace G by GH. Okay, H is some element of the group, I don't care. Pick any element, replace G by the element GH. So what do I get? Well, I get the new relation ai chi I of GH is also 0. Okay, and I think of G as sort of varying here. I'll fix H and think of G as varying across the elements of the group. So here's my relationship, and what does this imply? This says that, well, I have to use somewhere that chi I is a character, okay, that it's a group homomorphism, and now is the time to use it. So I'm going to rewrite this as chi I of H, chi I of G is 0. Okay. Now what does this mean? Well, I will reinterpret this equation as follows. This just says that this is true for all G in G, right? So it's almost like the original equation that I had. So this was my original equation 1, and from that I have obtained a second equation 2. In fact, I have obtained one such equation for every element H that I can fix. So from one dependence relation that I had, I have generated many more dependence relations. Okay, so observe, this just means that AI chi I of H. So I will rewrite this as a AI chi I of H. Think of that as a new constant times the function chi I is 0. Okay, so now I've removed G from this picture. Okay, so what does this imply? I have many different dependence relations among the chi I's, and therefore it allows me to eliminate. So I can now do the following. I can, from these, I can eliminate. So let's take these two, and let's eliminate chi n from this equation. So let's eliminate the last fellow. Okay, chi n of G, let's say. Okay, now what does that mean? Well, I'll have to multiply 1 by chi n of H. So how do I eliminate chi n of G from these two equations? I multiply the first equation by chi n of H, and I subtract it from the second equation. So to do this, I have to multiply this by chi n of H and subtract the second equation from it. Okay, so let's do that, see what we get. So here's what we will get. Summation I goes now only from 1 to n minus 1, because the last term is going to get cancelled, AI, and so okay, let's write everything out for the moment. AI chi n of H, chi I of G. This is my first equation with chi n of H multiplied minus the summation AI chi I of H, chi I of G goes from 1 to n. Okay, so this is what I get. So this difference is of course also 0. But now observe that the nth term in these two summations cancel each other. So this means that I can rewrite this as 1 to n minus 1 AI, and I get chi n of H minus chi I of H times chi I of G is 0. Okay, and this is true for all G in G. Now what does it imply? This is exactly a linear dependence relation between the first n minus 1 chi I. So this I can think of as, well, I'll just remove the G now from this. Think of it as a linear dependence relation which connects the first n minus 1 chi I's. Okay, so this is now an equation if you think of it in the vector space of all maps from G to F. Now what does that mean? We remember had assumed by induction that any n minus 1 chi I's are linearly independent, but here is a linear dependence relation amongst them, and so therefore all the coefficients have to be 0. So AI into chi n of H minus chi I of H have to be 0 for all I equals 1 to n minus 1. But we recall had said that the AI's themselves were all non-zero by the induction hypothesis. That means that the inside has to be 0. So we conclude then that chi n of H therefore equals chi I of H. Okay, and this is for I equals 1 to n minus 1. But remember, this is the important observation, H itself was arbitrary. We fixed H to be any element of the group G. Okay, so this arbitrary choice tells you that, well, as characters chi 1, chi 2, chi 3 are all equal to chi n. Okay, but that's a contradiction. In fact, it's our original assumption was that the chi's are all pairwise distinct elements. So chi n cannot equal any one of the previous ones. Okay, here we therefore get a contradiction. So that completes the proof. It shows that by induction we have shown that any set of pairwise distinct characters is necessarily linearly independent. And so here's a little corollary, and it is in this form that this will find application. So if K is a field, then look at the set OT K. Okay, recall OT K is just a set of all field homomorphisms of K. This is a linearly independent. So you can think of OT K as follows. This is a subset of all maps from K to K, right? All set maps from K to K. And as we just said, the set maps from K to K is a K vector space. So this is a K vector space. Okay. So the set of automorphisms is, well, it's not a subspace, it's a subset of the K vector space, and the claim is that this is a linearly independent subset of this K vector space. Okay, so it's linearly independent over K. So K is the only field here really. Okay, so we claim that any collection of automorphisms is, well, the set of all automorphisms is a linearly independent set. Okay, and well, the proof is rather easy. It just follows from the previous theorem that we have already shown. So observe that to show that a set is linearly independent just means you pick any finitely many out of them, right? You pick any finite number of elements from OT K and you must show they are linearly independent, right? So it's only checking only involves checking finitely many at a time. Okay, so let's pick finitely many automorphisms and show that they are linearly independent. So let sigma 1, sigma 2, sigma n be distinct. Okay, let's assume they're all pairwise distinct automorphisms, and you need to claim they are linearly independent somehow by using the previous theorem. Now, how do we think of them as characters? Well, they are maps from K to K. So observe that each sigma I can think of as follows. I will restrict sigma I to K minus 0. Okay, I will think of it as a homomorphism from the multiplicative group K cross to itself. Okay, so this is a group homomorphism. It's a group homomorphism. So if instead of sigma I look at sigma restricted to K cross, then this is therefore, this is a character. Well, this is a K valued character, right? So this is a K character, if you wish, of what's the group involved? Well, if group is just K cross. Okay, so by the previous theorem, therefore you can apply our previous theorem. By our previous theorem, conclude that, well, what do we conclude? That the collection of all sigma I restricted to K cross from 1 to n is a linearly independent subset of the set of all maps from G to K, and G here is K cross to K. Okay, but that's more or less all that we need, because observe that maps from K minus the origin to K and maps from K to K are, well, they're almost the same thing, right? So if instead of I mean, what do the sigma i's what's the difference? Sigma I restricted to K cross, and what's the extra point? K only has one additional point, right? K is just K cross union 0, and therefore if I know sigma I on K cross, then I know sigma I completely, because observe sigma I on 0 is 0, right? So sigma I on K cross, if you know that, and if you know sigma I of 0 is certainly 0 because it's a homomorphism. So these two determine sigma I. Right? This tells me what sigma I is. Okay. So in other words, and of course one has to check this, but the linear independence of So observe that the linear independence of sigma I restricted to k cross implies the linear independence of the sigma i's on all of k, okay, sigma I on k. And why is this? Because, well, how can it possibly fail? Only if it fails at the origin, right? So if there is some linear dependence relation at the, which somehow fails at the origin alone, but that's not going to happen. Okay, so this is an easy verification, so I should just say exercise maybe. This is one additional point, does not cause any problem. Okay, so this is an important result which will be used to prove Artin's theorem.